So you look up at those massive smokestacks pumping out exhaust, and you've got to wonder, right? Can we actually recycle all those carbon emissions? I mean, is there a way to take the very greenhouse gases that are actively warming our planet and somehow completely flip the script? What if we could actually transform them into the everyday stuff we need to literally build our cities and, power our planes? Well, that's exactly what we're looking at today. Welcome to our explainer on the hype and the reality of carbon utilization. We're going to dive straight into some fantastic, cutting-edge data from the Oil and Gas Climate Initiative, the Boston Consulting Group, and Carbon Herald. The big question we're trying to answer: can we actually pull off a circular carbon economy? Here's our roadmap for today. We'll hit the carbon capture promise first, then explore 4 key utilization pathways. After that, we'll run the numbers on climate impact and carbon math, face the reality of scale and cost, and wrap it all up with the 2026 CCUS outlook. Let's get to it. All right, section 1, the carbon capture promise. Okay, to really wrap our heads around this space, we've got to clear up a crucial difference between 2 major acronyms. We've got CCUS, which is carbon capture, utilization, and storage, and then CCU, which is just the utilization part. Storage is exactly what it sounds like, locking carbon deep underground forever. But utilization, that's the exciting part, where we capture CO2 from industries and actually recycle it. It's the whole basis for a circular economy. Right now, we utilize about 250 million tons of CO2 a year, mostly for things like enhanced oil recovery or making urea. But the future of CCU, it is looking way more diverse. Moving on to section 2, 4 key utilization pathways. So the folks over at Boston Consulting Group put together this comprehensive study, and they nailed down 4 incredibly promising commercial pathways that are expected to make a real global impact by the year 2040. We're talking about construction aggregates, CO2-cured concrete, e-kerosene, and e-methanol. Let's break down how these actually work and, more importantly, if they can scale. Now, what is super fascinating about this is that construction aggregates actually represent the absolute largest potential market by pure volume. Think about all the crushed stone, the sand, the gravel we use in construction all over the world. This single pathway alone could potentially utilize about half a gigaton, 500 million tons of CO2 every single year. But there is a catch. Digging up conventional rocks is just so incredibly cheap, meaning this really low-value recycled product faces a huge uphill battle to compete economically. Then we have CO2-cured concrete. Now, this is a much smaller market. We're looking at maybe 40 to 70 million tons a year. But the coolest part is the technology is practically ready to scale right now. When you cure concrete with CO2, you are literally permanently mineralizing that carbon directly into our buildings. It's basically a permanent storage solution that lasts exactly as long as the building stays standing. And that brings us to our 3rd and 4th pathways, which are the e-fuels, e-kerosene, and e-methanol. These are medium-sized markets, and they are specifically designed to power those stubbornly hard-to-decarbonize heavy transport sectors. Think aviation and massive shipping freighters. This pathway has the absolute game-changing potential to completely replace fossil fuels. But, and this is a really big but, to do it sustainably, the industry needs access to a massive amount of low-cost green hydrogen and biogenic CO2. Basically, we need carbon sourced from biological materials or pulled directly out of the air, rather than just recycling dirty fossil fuel emissions. All right, section 3, climate impact and carbon math. To figure out if these products are actually helping the climate, we've got to look closely at the product carbon footprints, evaluating them from cradle to gate, or even cradle to grave. We basically drop the overall climate impact into 3 distinct buckets. First up is removal, which is awesome because it actually increases our global CO2 budget by taking carbon entirely out of the system. Next is reduction, which just kind of slows down how fast we burn through that budget. And finally, avoidance, which has a completely neutral impact. If a product made from CO2, like a synthetic fuel, just re-emits that carbon when you burn it, well, you can imagine the accounting rules get extremely strict. Just look at the sheer variance in these numbers. Under the right cradle-to-grave conditions, e-kerosene can achieve a massive 98% abatement. Huge win, right? But then look at e-methanol. Its benefit swings wildly from 30% all the way to 98%, totally depending on where the CO2 comes from. And check out CO2-cured concrete. Its impact ranges from negative 100% to a positive 5% compared to standard products. That wild swing means if a plant uses highly carbon-intensive energy to make the concrete, it might actually emit more than it saves. On the flip side, though, aggregates offer true net negative emissions, securely locking away anywhere from 9 to 45 kilograms of CO2 per ton. So the math really matters. Which leads us to section 4, the scale and cost reality. Okay, I want to anchor these next few points in your mind with a very specific number: 50 million tons per annum. According to the International Energy Agency, as of early 2025, that is our current global operational capacity for CO2 capture and storage. Just 50 million tons. Keep that exact scale in your head as we look at what we actually need for the future. Because here comes a massive reality check. Even if every single one of the hundreds of announced global projects goes off without a hitch, our total capture capacity in 2030 is only going to hit roughly 430 million tons. But to actually hit net zero, we need 1,000 million tons, a full gigaton. We are currently sitting so far below the scale required to meet these climate targets, it's honestly a bit staggering. If you're wondering why that massive gap exists, you just have to look at the raw economics. Right now, e-fuels are sitting at 2 to 4 times more expensive than their regular fossil fuel counterparts. A lot of that depends on subsidies, but still, this incredibly high cost is largely driven by the massive amount of energy required just to synthesize them. Without some major regulatory mandates or massive financial incentives pushing things along, the business case for e-fuels is just currently negative. And we're seeing a remarkably similar story over in the built environment. CO2-based building blocks are facing some really steep cost penalties too. CO2-cured concrete is currently about 1.3 to 1.5 times more expensive, while those aggregates we talked about, they're 2 to 4 times more costly than just digging up normal rocks. Experts are estimating that to actually make these concrete products profitable, we'd need some pretty brutal carbon pricing, somewhere in the range of $125 to $175 per ton, plus massive landfill taxes, just to level out the playing field. All right, final stretch, section 5, the 2026 CCUS outlook. Let's trace some of these pivotal milestones starting in 2026 and looking out to 2040. 2026 is a huge year. We're expecting Denmark's offshore green sand storage initiative and the massive Stratos direct air capture facility down in Texas to officially launch. Then, by mid-2026, Germany is rolling out a massive $5.9 billion carbon contract scheme specifically to support industrial decarbonization. And looking a bit further ahead to 2040, the EU has already laid down the law that they're phasing out fossil-based CO2 for synthetic fuels entirely. They're only going to recognize biogenic or direct air capture sources. So this timeline clearly shows how major government policies and multi-billion-dollar funds are stepping in to actively force this market forward. But here's the thing. Actually capturing the carbon, that's really just step one. Building out the transport pipelines and the physical storage infrastructure is the next critical bottleneck we have to solve. Get this, roughly 70% of global industrial CO2 emissions are located within just 60 miles of potential storage sites. So connecting those dots with really robust pipeline networks and cross-border shipping routes is absolutely essential if we're ever going to achieve economies of scale. I really want to emphasize this quote from Yami Burrows. He's the global segment lead for CCUS over at DNV. He says, the industry's next challenge is to scale up, deploying more projects and deploying them faster. And that just hits the nail on the head. It perfectly reinforces the core message from all the data we've combed through today. The technological foundations are basically ready to go, but the pace of commercial deployment absolutely has to increase, and fast. So the science works. The pathways to actually utilize this carbon definitely exist. But given those steep 2 to 4 times cost multipliers we just talked about, it all begs a pretty heavy question. Is society willing to pay the premium required to turn carbon recycling into a global standard? Ultimately, how much are we truly willing to pay to achieve our climate goals? Something to think about. Thanks so much for joining me today, and I hope this gave you a much clearer lens on the true state of carbon utilization.